In this lecture, we are going to learn something about liquid-liquid extraction. As I said in my first lecture, I almost wrote everything that I want to talk in this lecture. So practically, I'm repeating what I did for the last half an hour or 40 minutes. So, so what I'm going to say is like, let's put a box. So that's what I'm going to talk about, liquid-liquid extraction. So if you want, you can call this is an unit operation. Almost every pharmaceutical industry rely on this technique. And why do we need to use this technique? The whole idea is to separate one component which is completely dissolved in a solution using another liquid, so which we are going to call this as solvent. So what's the whole process will look like you are going to deal with two different type of liquids. So in one liquid you have some component which is your solute, and that's the component which we need. It can be a very important pharmaceutical ingredient like antibiotics or some vitamins. So that's the compound which is completely dissolved in a liquid, which means if you look at the solution, it's going to look like a transparent. It won't be even like a cloudy solution. So completely dissolved. So your product is dissolved in some solution. And then what we need is we need to separate that product from that solution. For that, we are going to purposely add one more liquid, so which we are going to call it as a solvent, and then we are going to use this solvent to take that product which is dissolved in another liquid. So that what we are going to do is like, imagine you have a solution with a very tiny bit of some pharmaceutical product. So you are going to add a bit of solvent and you are going to concentrate that the whatever the solute which is dissolved in the another liquid. So that's what we are going to do. So and this whole process we call it as a liquid extraction process, because you have two liquids and you are extracting something from one liquid using another liquid. So your liquid is going to do the job, you know? So this is a very complex process. It's not that easy. Like if there is a system, you have one solid and one liquid, it's very easy to imagine. But if you have two liquids, then you should pay some attention. Yeah. So how to explain this process? In a simple possible way, I always try to imagine some experiments. So that's what I did. So what you do is like you have a reactor which I showed here. So just assume this is your reactor and you have some carrier. So this is your carrier liquid, and whatever the green dots that you see inside, let's call them as a solute. So what you have is like you have one liquid. That liquid have lot of solute particle which is your product of your interest, and we need to separate that product using some other solvent which is again some liquid. So you add some solvent which I showed here in the pink color. So this is your solvent. So what we are going to do is like you are going to add that solvent and we are going to try to extract your solute which is dissolved in the carrier liquid, and you are going to move them to the solvent. Yeah. So what, and always keep it in your mind that we are going to use some terminologies like you have a liquid and liquid. I already named one of the liquid as solvent, and the liquid which is which contains your solute particles in a completely dissolved state. So we call them as a carrier liquid. So use the terminology carrier liquid, and whatever the product which is dissolved in the carrier liquid, we are going to call them as a solute. So you should pay attention to these names, because when you are going to ternary diagrams, we are going to use the same terminology: solvent, carrier liquid, and solute. So these are the three different compounds that should come into your mind whenever we are going to talk about a liquid extraction. Yeah, so that's what I wrote it here. So let us call this component which is completely in the dissolved state as a carrier liquid. Yeah, so that's your carrier liquid. See some spelling mistake. So you have a carrier liquid, you have a solute, and you have a solvent. So that's the initial setup of this experiment. So so you have an experimental setup where you have a carrier liquid, where you have a solute, and now our goal is to remove that solute. We have to concentrate them into some other liquid. Yeah? So we will come back to that, like why it's already in a liquid, why do you even transfer it to the another liquid? There are so many good reasons that I will tell maybe at the end of this lecture or maybe in the next lecture. Yeah? So that is the purpose for doing this job. So what we are going to do now is like we are going to add some third component. Third component is nothing but another solution. So in this case we already named, which is a solvent. So we are going to add a solvent on top of this your carrier liquid. So what happens after that? So always try to remember that I put a note, even I shouldn't forget. So try to remember that you have the starting solution where you have your carrier liquid, where your solute molecule is completely dissolved. It's not even dispersed, it's dissolved, which means completely dissolved. If you put a light on other side of that liquid, you can see that it will completely pass through. So that's the meaning of completely dissolved state. So it's completely dissolved, and which means solute and your carrier liquid, it's completely miscible. That's an obvious statement. So that's why it's completely transparent, and we call them as completely miscible. So that's your initial state. At the beginning of your experiment, you have some solution which contains two components. One is solute, and which we already named it as a carrier liquid. So if you want, you can call this as a carrier liquid plus solvent. If you want, you can call them as a feed mixture. Feed mixture is in a liquid extraction process is nothing but something that contains a carrier liquid which carries your solute, exactly. And then there are few things you must remember when it comes to liquid extraction. Your carrier liquid and your solvent that we are going to add, which is your second liquid, it may be immiscible or may be partly miscible. So keep that in your mind. And the next thing you should remember, solute plus solvent. So solute is the product that we want to separate from the carrier liquid or from the feed mixture, and then this solvent, this should be completely miscible. So keep that in your mind. And then your carrier liquid and your solute, this should be miscible. This is an obvious, stating the obvious. So that's why I put this obviously that's what I wrote it here. And then what you need is like so let's go back to this setup here. So we already have you have some solvent order. This is your feed mixture, so you can agitate it. So once you agitate it, what will happen is like you are going to mix these two solutions. So it will help to it will speed up your mass transfer process. So what will happen is like that solute molecule which is dissolved in this one here, it will transfer it to the solvent particles. So I think I wrote it here. So your solute will be transferred from the carrier liquid to the solvent, and at some point you will come to an equilibrium stage. So I hope you all know what's meant by equilibrium stage. So if just imagine you have some facility to monitor the concentration of your solute in the solvent and the concentration of your solute in your carrier liquid or in your feed mixture. So it will decrease. This is in your carrier solvent, so that's in your solvent. So it will continuously increase. So what's happening is like some physical process is happening. It's not a chemical reaction, it's purely a physical process. So you have a lot of solute in your liquid in your feed mixture, and there is nothing in your solvent, and your solvent can take your solute because both are miscible. So due to some concentration gradient, your solute will move from this high concentration phase to the low concentration phase, which is your solvent. So that's what it's happening. So it's purely a physical process, and that's happening due to mass transfer effect. And mass transfer is happening because you have a concentration gradient inside the reactor. So equilibrium is some point, say like say this line, you can call this, that's the point. You can say that system reached an equilibrium as you see the concentration of a solute in the solvent and in the carrier liquid, that is it remains constant, so which means eventually it reached an equilibrium. Yeah? So I hope you all know what's a mass transfer process. Yeah? So mass transfer is a physical process. It's a one-way process. It can go only in one direction, and that direction will be from high concentration zone to low concentration zone. It cannot come back to the in the opposite side. There will be no transfer of anything from low concentration side to the high concentration side. So, and it's a purely physical process. All you need is that a bit of a concentration gradient, and that will do the rest of your job. So that's the whole principle behind the mass transfer process. Yeah. So what happens at equilibrium? So let's go back here. So once your system reached to an equilibrium, so you will have that solute molecules must have already moved from your carrier liquid side to the solvent side. Yeah. So and one more thing you should remember in your when it comes to liquid extraction is like there will be a density difference. So this is your feed mixture, this is your solvent, and your solvent will be on top of your carrier liquid or your feed mixture, and that happens because due to the density difference in the solution, and this will remain the same even after the equilibrium is achieved in the system. Yeah. So after even after you moved your solute from your carrier liquid to the solvent side, still your solvent will remain on top of your carrier liquid. So which means you will see a clear interface somewhere here. So all you can do is like you can put them in a separating funnel. You will see some interface again at this point. So once you open the tap, you can separate this liquid and then you can separate this liquid. So this liquid will be enriched with a, let me change the color. So this top of your liquid you can collect using a separating funnel. So this will have a very high concentration of your solute, so which is the product of your interest. So I hope you all understand what's the concept behind liquid extraction. So you have two liquids and we have three different names. So the first liquid we call it as a feed, and you have two names for it. It has two things or two components inside. One is your solute, that's your product of your interest, and that's carried or dissolved in the carrier liquid, and we are going to add a solvent. So we are going to move that solute from the carrier liquid to the solvent using a physical process which we call it as a mass transfer process. Yeah. So that's the whole thing. Just let me highlight here. So usually the solvent side will be on top of your carrier liquid, so which means you can easily physically separate these two liquids. So that's what I stated. So you can physically separate these two liquids using a simple settling tank, or if you want you can use a separating funnel. So that's what I stated here. So let's go to so at the end of the process, you will notice a clear phase separation, and you will notice the clear phase separation because it's our job to select what type of solvent to use. If you think your solvent is not going to give that clear phase separation, it's not a good solvent anymore for liquid extraction. So we will come back to this in the next lecture. So what type of solvent we need to select for to do this job, which is the liquid extraction. Yeah. So we will come back to that one, but at least for the moment you should have some idea that there should be a clear phase separation. So only then you can physically separate one liquid from another liquid. So liquid extraction is not just about mixing two liquids, but it's also about extraction involves you mix them, you transfer solute from the carrier liquid to the solvent, and then you settle them. Once it reached an equilibrium, you allow the liquid to settle down, and then you separate both of these liquids. So all this process all together we call it as a liquid extraction. Yeah. So it involves like intimate. You are doing something to to provide some intimate contact between liquid and your your feed mixture and your solvent, and then followed by settling, and then followed by physical separation of these two liquids. Yeah. So once you separate your solute in the solvent, you can separate your solute from that solvent using a simple drying technique, or you can go even for a bit of sophisticated technique like a distillation technique. So distillation is a very complex process, but we will come back to this in the next once we finished with liquid extraction. Yeah, first you should know what is liquid extraction, and then we will go on to distillation. Distillation is a bit more easier than liquid extraction. So I took this topic as in the beginning because it's bit tough, but if you manage to understand liquid extraction, the other unit operation will be just like a peanuts. Distillation will be more easier than this, adsorption will be even more easier, crystallization will be it's a bit easy. You will work with we will come back to this crystallization later. I'm not going to talk now. And then I just put like at least I will ask, you might ask, why not to dry the solution directly and from the carrier liquid and then separate the product? As I said to you, like so you have a starting solution with solute already, so we can directly, you can just heat, dry, evaporate everything, and then take the solute product. That's one way to do it. But why we are not doing that, there are many good reasons. I will tell at the end of this lecture, but for the moment I will tell one easy reason. Like, imagine if your compound, your solute is dissolved in water, which is the normal solvent which they commonly use in any fermentation processes. Yeah. So, and if you want to separate that product using a simple drying technique, you have to heat the solution to 100 degrees centigrade. And if you have something, say like a penicillin or any other antibiotic or any other cell like any other microbial products that we are interested in, maybe once we reach to the 100 degrees centigrade, which is the boiling point of that water, everything will get killed inside. So the best idea is to, you can transfer that solute into some other liquid which might have a very low boiling point, where so that you can heat that liquid at mild temperature, which won't kill your product or which won't degrade your product at the temperature. So that's one good reason when people go for an liquid extraction. So that's the main reason people always prefer in many of the pharma industries. They prefer liquid extraction, and penicillin, when they manufacture penicillin, liquid extraction plays a very big role. Yeah, so that it helps to separate the product from the fermentation broth to your solvent side. So I'm going to upload a separate YouTube video. You must watch that video, and then next lecture I'm going to talk a bit about that video, how they manufacture penicillin. So the video which I will upload in Sulis, you will not listen any sound or anything. So but I think it's some cartoon image or like an animation created by someone, and it shows how the penicillin is manufactured and how it's extracted using a liquid extraction technique. There you will see some name of the solvent which they use to extract the penicillin from the fermentation broth, or to concentrate the penicillin from the fermentation broth to the solvent side. So it's your job. You must look into that YouTube video. Don't skip that. You might have some objective type questions based on that video in the final exam. Yeah? So extraction processes reduces the cost involved in drying and also distillation. So as I said, like if your solution, if you want to heat it to a very high temperature, which means you also need to spend a lot of money, so you can minimize the cost if you manage to move your solute to some solution that you can boil at slightly lower temperature. And this distillation, we will come back to this when you're going to talk about distillation. So how I'm going to do this lecture is like, we finish liquid extraction and then we go to distillation, and once we finish both, we will try to compare both of this process a bit here and there. So what are the advantages of one process, what are the advantages of the other process, with So that will give you some idea about the advantages and the limitations of both of these techniques. Yeah, but both of these techniques are amazing techniques, and they are used in almost every pharma industry and almost in every chemical industries. Yeah, so most of the chemical industries, especially petroleum refining and few other things. Yeah? So I already stated this. So where we use the liquid extraction, one is the penicillin recovery from the fermentation broth. And I think this is a good time to define what is a liquid extraction. So that's what you're going to define. Whatever I talked so far, based on that we can define what's a liquid extraction. If I ask this in the exam, you should know, or even in any interview, you should know. If somebody asks what's a liquid interaction, so that should be your answer. So it's purely a physical process, no chemical reaction, so the energy involved are very low, and it's purely a mass transfer operation. So mass transfer happens from one side of your liquid to the other side of your liquid. So when a solution, or I said we can call this as a feed. Feed contains a mix of a carrier fluid and solute. So when you bring that feed in intimate contact with a second immiscible or slightly miscible liquid solvent to achieve the transfer of your solute from the feed side to the solvent side. I think I draw this picture already. So this is nothing but your solute concentration. So this is your solute concentration, the top curve, that's your solute concentration in the solvent, this one, and that's your solute concentration in the carrier liquid. So at this point it reached an equilibrium. Yeah? So that's the point of equilibrium. I highlighted it here. So which means the system is already reached an equilibrium, this whole zone. So that's the same setup we started at the experimental setup. So at the end of once your system reached an equilibrium, you will see something like that here. You see the solid particles I showed in green here and there. So after equilibrium, most of the solid particles already moved to the solvent side. So now you can remove the solvent. From there you can recover your solute. So using any other techniques. Some of these techniques we are going to learn in this module. It's not only about distillation or simple drying. We also need to go for other technique for further purification, like chromatographic separations. So those things we will come back. So there are a lot of things to learn in this module. Yeah. So and few things. Now you have some few terminologies again. Whatever the solute rich phase, we call them as extract. We are going to name it as extract. So this part, so that part is, so this is your extract. And whatever the starting feed mixture, now it should contain less amount of your solute, or you can call it like a remaining solute or left out solute after equilibrium. We are going to call them as raffinate. So that's, you have some extract, you have some raffinate. So that's how it's going to look like. So I try to draw like a chemical engineers. What we do is, like, if you don't know anything to do, if you have some process, if you are not good in, if you don't know to draw the reactor or the whole unit, all we do is, like, we put a box. You make a box, and then some feed goes inside and something comes out. So this is too big. So this is your feed, and this feed contains your carrier liquid. It also carries your solute. So solute is the product that we want to separate, or we like to separate. And then you also supply some solvent. So that's the guy who's going to do the job. So solvent is going to take most of your solute, and then you take the solvent out that contains a lot of solute and maybe a bit of a carrier liquid. Yeah. So, and then we can separate them using a drying technique or a distillation technique, or we might even go for further product purification, and then we might even go for recovery of solvents. Here comes the distillation and other processes that we are going to discuss later. And then your feed solution, that since we already transferred a lot of solute molecules from the feed to the solvent, here. So the residual, whatever the liquid that comes out, so this is, we can call it as a residual feed solution, and this feed solution may contain a, or not this one, sorry, it's not carrier liquid, it might contain a bit of solvent. And your carrier liquid may be slightly miscible, so you might see some solvent here in the residual feed solution. Yeah, so and if you want to recover the carrier liquid, or if you want to recover the solvent, then we can go for the process which we will call it as distillation. So so that's the whole process. Yes. So why I showed this diagram, I will tell to you why this diagram is really useful. Yeah, so this diagram will help you to get some idea about the process economics of the whole extraction unit. Yeah, so you have feed, you have a solvent, your solvent takes your solute, and then it goes on for further job, which is like you might go for drying, or you might go for distillation, you might go for product purification. We like to recover the solvents because solvents are so expensive, especially at industrial scale. Yeah? Like imagine if you have you are extracting something using like 10,000 kg of your liquid, then you cannot dispose that solvent after extracting. You have to reuse that solvent to save a lot of money. Yeah? So that's how recovery of solvent, all these things becomes really important. And for recovery of solvent, we go for other techniques like evaporation followed by condensation, or distillation techniques. So whenever we talk about extraction, and whenever you think about the money involved in the liquid extraction, you should think about all these factors. Yeah? So that's why I made this diagram for a reason. So now go to the next part, which I typed already here. I wrote it here. So the transfer of solute from the feed solution to solvent can be achieved by bringing the solvent into intimate contact. I'm going to stress this point, intimate contact. So I will try to make a small video on this one. So intimate contact is like if you look at the setup, if you look at the starting setup, you have your feed mixture and then you have a solvent. Yeah? So there is only one boundary here. So if there is some mass transfer to happen, it has to go through this boundary from here to here. So if this boundary is small, if you have only one boundary here, which means only few mass will go from this side to that side. But if you create a lot of interface, then which means, so you have some interface, you have some solute here, and you have some solvent here. So it has to pass through this interface. So if the interfacial area is higher, which means more solute will move from solute side to the solvent side. So what we do is like we agitate using some impellers. Yeah? So impeller might look like something like that. So it will create some tiny droplets of your solvent that will be dispersed completely into your liquid. So what it happens, suddenly you will see a lot of interface around each of those bubbles. So your mass transfer can happen very easily. So from your feed mixture side or your carrier liquid, it can go easily through this lot of available interface, and it can enter into your solvent side, which means your mass transfer will become so rapid, and we call them as intimate contact. So you should figure it out some way that can provide complete mixing or provide that intimate contact, record level of intimate contact, so you will quickly transfer your solute from your feed mixture side or from your carrier liquid to the solvent side. And why do we care about the speed? And that's because, like, imagine if you have a process, and if you don't mix that, if you don't give that agitation, it might take a day. But once you provide some agitation, so you can transfer you can finish this whole extraction process within few minutes. So then, and then you can clean the reactor, and then you can go for the next batch, which means you can increase your productivity. So that's the whole idea. This is not a chemical engineering principle even, this is the normal common sense. So what's the key advantage of making the process bit more faster? So that's the whole idea. This one I already stated few times. So at equilibrium, the solute rich solvent phase will be on top of your residual feed solution, so that allows you to physically separate these two liquid mixtures. And obviously these two liquids are on top of, so the second liquid is on top of the first liquid, and that happens normally due to a density difference. So everybody knows this principle. And a bit of economics. This is the good time to tell about the process economics involved in extraction. As I said to you, like, it's whenever you go about talk about liquid extraction, so whether you believe it or not, 15% of the money that you spend, that goes for your extractor. You buy the extractor and then you do the job, and then once you finished your extraction process, you have to go for solvent recovery, product purification, and so many other things. And for that you have to invest the remaining 85% of your cost. Yes, like to install a distillation unit, for example, that allows you to recover your solvent with a decent level of purity, or the other process like a chromatographic separation for further product purification. So whenever if I ask some question about the process economics, you have to talk a bit about how much cost goes into the extraction process, and how much cost goes into the other downstream processes. So you must have some idea. I just put a key, so like a small note here, like when we use extraction instead of distillation. Obviously we didn't discuss distillation so far, so we will come back to this. We are going to learn many things about distillation once we finish this topic of liquid extraction. And for the moment I will quickly say there are few good reasons that you should know. I already mentioned about this one. If you're going to deal with heat sensitive materials, these antibiotics and these vitamins, they're very sensitive to high temperature, or maybe like any proteins. So it will lose its structure. Proteins are more happy at some optimal temperature. Once you heat the temperature, they will lose its structure, and it will lose the properties of proteins. Like proteins like to have some binding packets which we need for so many good reasons. And once you increase that temperature, the protein will lose its structure. They call it as denaturation of protein. And if you're going to separate some proteins using like liquid extraction technique, then it's better you go for you use a liquid extraction technique instead of other techniques like distillation or others, or a normal evaporation process. So, and then another thing is a dilute solution. Just this is a very good thing you should remember. Imagine you have a solution with very low concentration of your some antibiotics. So and if you want to evaporate it, you have to evaporate it for a whole day. Imagine like you have a tiny bit of some compound dissolved in a very large volume of your solution, and if you want to evaporate it, it's going to be like it's doable, but you have to spend a lot of energy to evaporate everything, and then finally you get some dry product. But if you can transfer significant amount of those mass which is dissolved in that solution, dilute solution, to a small volume of your solvent via liquid extraction, then you can evaporate the tiny bit of solvent, and then you can take the pure product from the solvent. So that's one good reason. I don't know whether you understand or not. I'll just draw some diagram. So imagine you have a very large volume of some solution with some solute particle, and you have a tiny bit of your solvent. So if this solvent can take the solute particles from the solute, and if it can concentrate, and after equilibrium you can take this tiny bit of solvent and then you can evaporate them, and then you get your product. So this way you spend less energy. So that's the meaning of this. And then here are few more stories. Like extraction is widely used in petrochemical, pharmaceutical industries. Classical example is penicillin, and to to extract penicillin from fermentation broth, which normally contains water. So water plus your penicillin. We use amyl acetate or butyl acetate as your solvent, and then we separate or we concentrate penicillin, yeah? And then obviously it goes through a lot of other techniques like chromatographic separation, distillation, and so on, or we will come back to that later. So that's the main reason we are studying this topic. And then finally, why all these beautiful things are happening, yeah? Like why sorry why when you mix two liquids and then something is transferring from one liquid to another liquid, and why these two liquids have a phase separation, why these don't two liquids don't mix with each other, but it allows to change a solute from one side of your liquid to the other side of the liquid, obviously via mass transfer. So everything is happening for some reason, yeah? And that reason, if you want to know the inner details, or if you want to understand how the solute is transferred from feed to the solvent side, or when it reaches an equilibrium, or how to know how much mass will be transferred from your liquid side to your from your carrier liquid to your solvent, or something like when the system reaches an equilibrium, or okay, not this part, and what type of liquid we know to select as a solvent. To answer all these things, so we must learn something we call it as a liquid-liquid equilibrium. So this is the one that we are going to cover in the next lecture. So I'm going to stop recording this video now. So in the next lecture we will cover about liquid-liquid equilibrium, and then we are going to draw some ternary diagrams. I'm going to show you how to get some idea from the ternary diagram and how to draw the ternary diagram, how to label your components on the ternary diagram, and I will tell where will be your solute, solvent, and your carrier liquid in that diagram. And then I will show some easy way to interpret the ternary diagram, like you have three components, which components are miscible and which components are not miscible. So we will get some idea, like so the next class will be more like a tutorial plus lecture, because I'm going to show you like line by line how to draw the diagram. So if you have a ternary diagram with this type of pattern, which two components mix with each other, so give me the answer. So those type of things. So that's those topics will be covered in the next lecture, and probably we need two more lectures, yeah? So next and next to next we will cover liquid extraction, and then we will also try to solve maybe one or two problems, yeah? So those will be like exam type problems. And always keep in mind that since the exam pattern is completely different from the previous year, don't expect that you are going to see some questions that are already asked in the previous years. I don't even have a copy of those question papers. So whatever you are going to get in the final exam, that will be something based on what I'm going to deliver from my side, yeah? So keep that in your mind. So thanks for listening. Let me stop recording this video.